Hello, Kuldeep.
Okay, hi, I'm
Yes.
sharing my screen. Okay. Hello, everyone. I will be discussing graph data models today. In our previous episodes, we have discussed about what are data models and what are the different levels of modeling we have to do. So, moving on with that, today let's see how graph data models work and what are the integrities in them. To start with, let's see the agenda for today. At very first, I will be discussing a small evolution of data models from where it is started and from where it is now. Okay, through the years, through the decades, I would say. And then we can move on to actually understanding what graph data models actually are. Okay, and after that, we will be looking at why there is a need of graph data model and why should we use it actually. And then we can go into a little bit a technical thing of how to perform actually a graph data modeling. Okay, and what are the things to consider while doing those things. Then we'll be discussing when is a when graph data models should be used, because there may be cases where graph data model looks fancy but doesn't satisfy everything which we need. So we have to understand when do we need a graph data model and when not to. After that, I will be quickly going through the current available graph databases and where it stands with all the performance and complexity and all those things. Okay, so let's start with so evolution. The data modeling evolution started in 1960s basically. Before that, computers are only considered as a giant calculators. So in 1960s, the need aroused that the real world entities and the real world scenarios have to be stored in some way so that they can be looked upon and queried upon. So in order to map a real world entities or scenarios to a computerized format, they need a technique, and that technique they called as a data modeling. So the evolution happened actually in four phases. The first phase was basically many things happened in this phase, but the most prominent were network data model, hierarchical data model, inverted list, and at the end of this phase, the object-oriented databases are also started to come up. Okay, so basically in these things, they only want to visualize how real-world scenarios exist, and then convert them into a format which can be stored into the system. Okay, so these are the major evolutions happened through the year. So if you see, IMS came about in 1968, which was an hierarchical database, and then in 1970, a theory was published about relational data model for large data and banks actually. So by that, the ER modeling which we must have used in our careers came about in 1976, and then the Oracle and Ingress. IBM DB2 in 83, and Cognito, which was one of the first in-memory stores, came about in 1989. The second wave started around 1990. Sorry. Uh, so the second wave was called the relational wave, where this relational databases and all the modeling techniques, all the querying techniques are getting evolved and grown into a space where huge data quantities can be stored and processed, and a lot of things can be done there. But they started to lose their users by 2000, beginning of 2000 somewhere. At the same time, the decision support wave, where the big analytical queries like online analytic processing and very specialized DBs for a specific purpose started to come up also. So here are the few. So Red Brick Warehouse came in 1990. Okay, UML in 1996. I'm just highlighting the things which we have used in our careers. Okay, and W3C RDF, the theory was published in 1999. Okay, so after this, the last wave was the NoSQL wave. Okay, so here actually in this decade, a huge shift happened from what was existing a relational model and how people used to understand and save data. That shift started from here to save it and model it in many different ways, which suits the scenario for which an application or for which purpose the modeling is done. Earlier, for any scenarios, the modeling need to be done by the way databases can store. But now modeling was more focused on how to capture the real world complexity. And then let's see which of the best we have to store that information into our system. So in this wave, the Neo4j came in 2007. Okay, Mark Logic in 2003, and the SysMe, the first Aduna SysMe, the first RDF database, which came about in 2002. And now we are seeing in Apache Spark, Hadoop, HBase, all those things came up quite later. And till now, major developments have been going on this field. Okay, and GraphDBs started from 2008, and then they realized the importance of graphs and graph data modeling. And it became popular from 2008 and is being heavily used at various levels of data modeling. Uh, okay, so is it clear till now? Should I move forward?
Yeah, very good, Kuldeep.
Okay, so moving on, what is actually a graph data model? So this is just a simple example of Amazon Web Services. So you can see here there is a region which is located in a continent, has an isolated availability zone, offers services, and charges applied on that thing. So this is a very simple model for an AWS EC2 service. Okay, and using this model, let's say if I have to ask a question that which is the cheapest EC2 service available in North America. Okay, so if you see this query is quite complex, though it's a very realistic real world scenario. But trying to convert it into a mechanism to save and retrieve data is complex. But through graphs, it became very easy because the relationships take precedence. So we from there we know that continent, okay, North America, what are the regions available, and then what are the prices there which are servicing EC2 instances, and we can get the answer of the query in a very uh, small amount of time spent on it. So this is actually a graph data model, okay, where entities, the real world entities, are represented as nodes, and the relationship between them is not denoted as a directed lines. So one node is connected to other node through a directed relationship. Let's see one more example. So this is basically a simple relational model where organization has a department and a person and a project. Okay, and there are few relationships between them. Okay, now if I have to convert this into a graph data model, it can be done like this. I have four entities denoted as node: organization, department, project, and person. Okay, and then the directed relationships can answer all the queries which can be answered by here in a much simpler and much faster way. And the most important point is much easier to understand here rather than here. So, any question from these two examples? Okay, so now let's try to define what actually graph data modeling is. So, so So graph data modeling is a process where user describes an arbitrary domain as a connected graph of nodes and relationship with properties and labels. So I will come to later what actually the nodes, relationship, properties, and labels are. But the concept here is that any real world scenario, if it is able to uh, model it in a certain way where nodes can represent an real world entity or a complex data structure, I would say, and those nodes are connected with a relationships which can have their own properties as well. So if we can model that, create a model out of this, then it's a more natural way of seeing a real world scenario. And because of the technology now available, it can directly be stored as such as well. Okay, let's look at a more technical or more detailed definition, which says that model in which a data structure or the schema or instance can be modeled as directed, possibly labeled graph, where data manipulation is expressed by graph-oriented operation. Okay, so basically, with this definition, we can categorize graph data model into a broadly three categories. One is representing a data or a schema with the notion of graph, or the data manipulation, which we used to do like nearest path or graph patterns or connectivity. Those kind of operations is expressed through graph. That's the second category. And third category would be the integrity constraints. So integrity constraints, if I explain to you, if you want to update something, okay, so we can put a graph, small graph model to execute all the integrities, all the updates happening to go through that graph before the actual thing is updated. So that which is to ensure the consistency of updation or deletion of any node or data from the database. So these are broadly three categories. The majority of data modeling is done on these two things, and these are actually handled by the physical data modeling layer. Am I clear till now, or I'm running too fast?
Kuldeep, can you give some example of nodes and relationships?
Yeah. So I will come to this in the how part. Okay, so if we go into this, so this is actually a node. So this every entity. So here we see that there are four entities, right? An organization, a department, a project, and a person. Okay. So now in the graph data model, a node is an actual entity in the real world. So person become a node, project becomes a node, department and organizations are also nodes. And the connection between them, which is let's say organization contains department, a person works for a department and and led by a department. So these are the actual relationships between person and department. Okay, person is also related to a project, which we consider it's a dedicated to or assigned to or working on. So this is also a relationship between a person and a project. And the project is owned by a department. So these directed lines are actually relationship between the two nodes. Did that answer your question, Arya?
Yeah, it does. It does.
Okay. So I hope what is data modeling is now clear to all of us. I mean,
Kuldeep,
as per definition.
sorry. Kuldeep, in your previous slide, can you go? So in this, I'm just trying to see what are the differences I'm seeing between the normal relationship diagram and this graph data model. What information is giving me? What information is coming from graph mode? Is the relationship between the tables, not the table, the entities, is it?
Yes, the relationship is also currently these tables let's say project member, department member, these department member, these are not actually the entities. Okay, so these are intrinsic relationship which we create to relate these two, right? So
But
these,
ideally, I don't think there is a need of these three white tables here anyway, because these are these can be handled through primary and foreign key, I think. Raja means in this example, uh, how we can see that graph is helping
Yeah,
more.
I think the left-hand side is there's one way to represent relationship as another table, which
Yeah.
basically connects two tables. The other way is like you mentioned. Obviously, you can have organization ID in the person table and person ID in the organization table, and you can set up a foreign key primary key association.
Mhm.
But I think what is lost here is the meaning of the relationship. The moment you say two tables are related by this particular foreign key,
Yeah.
that it is not a semantic meaning in that relationship. It is just a primary key foreign key
We cannot
relationship.
understand that who is part of what, like what is the direction of the relationship, right?
Direction also you will know by saying that the primary key of this table is a foreign key in that table, and therefore the direction of the relationship will be evident. But the meaning of the relationship, for example, here in the right hand side, we say person works for a particular department. The
Mm-hmm.
works for here is the meaning. Now, I think one key differentiator in the data models is that the semantic meaning of the data in the left-hand side is left to the application level. I mean, at the table level, at the data model level, we just say two entities are related with the foreign key, primary key, but the actual meaning of the relationship is known to the application or the developers only. But on the right-hand side, the data model itself has that semantic meaning of how these entities are related. So, so
This is
that
more
that
of
to me.
presentation of like presentation of the application or actual implementation then.
Hmm.
It
Yeah.
can be
So
the actual implementation. I think one on
this
the
one.
left also. The one on the left also. I mean, why these kind of tables might exist. One basic example of this could be some master tables. For example, in some cases we might not be. Uh, I'll just take one example from this MSISTN to IMSI master,
Mhm.
which is a global list which just exists, and two tables they can basically relate to each other through that list.
But we don't really need it, right? If IMSI is there in
In
the
some cases we might need it because there could be some tables which lack the IMSI or which lack the MSISN for that matter.
that you when you are putting into the table itself, then only you merge this two and you do it, right? It means you look up and do it. But at the end to the application, it should not be visible. There is a way to do that, right?
Yeah, it might be, but I'm talking about the existence of them.
so if I mean, if you look at the human perspective, if you look at two relational tables connected in a certain way, because we know what person means, we know what organization means, and therefore, by human inference, we know what is the meaning of this relationship.
Mhm.
But the where the future is to have machines automatically understanding and inferring something from these relationships. In such scenarios, the data model must have more declarative meaning of the relationships, and that's what the graph data models are providing actually.
Yeah.
Mm.
If we are reading through random data,
Mm.
unstructured data, and trying to get out the relationship between the entities and all
Mm.
that,
Mm.
maybe.
Exactly. So the data model must becomes more complete if
Yeah.
it has the semantic meaning of relationships within the model itself. So it becomes complete that way,
Yeah.
and then it becomes even for humans as well as for machines to make some inferences in a non-ambiguous manner. Okay.
Kuldeep, you were saying that this graph data model is in nodes and the relationship and with the properties and tags. Can you show me the properties and tags in this? Is this listed here? Are those listed here?
Uh, uh,
But I can.
okay, I will tell you, but I will cover that thing into the how part.
Okay.
But here actually, if you see this role member one is actually a property of this relationship. These three, title, start date, end date, person ID, first name, these are the attributes of the person.
Okay.
And person itself is actually a label. So you can label a node with more than one labels. You can say it a person, or you can say it a author also. So these labels will decide which relationships to take. So if you just say a person, I mean, if you say a author, you can then follow the author kind of a subgraph to maintain that. Those features are available in
What is the difference between node and tag then?
node and tag. Label is just a label for that node. So this node is actually an entity that is labeled as person or author or anything else.
So
So
is it
these,
like this, like a manager or a author or anybody can be a person? So person becomes
yes,
a node, but the label
yes,
is manager and author.
mm, yes.
Okay.
Okay. So moving on quickly to the why part. So I mean, we have already discussed few advantages of why graph data models are needed and actually why graph models are helpful. So the basic difference is the focus is on relationship and data interconnectivity. In all the relational models, the entities and their attributes and what all information they can contain, those take much higher precedence than anything else. Relationship is a second class citizen, which can be managed by different ways. But here, both of them are on the same level. Relationships between data also take precedence. Okay, so the second thing is it's the most natural way to understand and
Actually,
model.
I don't understand the first point.
Okay, what did you understand?
Means, can you just elaborate by example? Because
Uh,
maybe.
exactly, that's what we were discussing in just one slide before here, that relationships are also considered here. Here, relationships are not actually that important. We can do it like this way, or we can do it like a primary foreign key way also. Here, the project, the person, the entities take much higher precedence. Okay, and while querying also, you don't take relationship into consideration. If you have to do, then you can either go by this way or use the foreign key to get the relationship. But relationship are not as at the same level as the entities itself. Here, both of them as the same level. Same
But
level means you can query or design a querying mechanism by relationships also. Here
okay,
you cannot design a query mechanism based only on relationship.
okay, that's what I was.
Okay, so it's the most natural way to understand and model because as we see in the real-time world, we can actually draw it, and that actually becomes a graph data model which can be realized in a physical storage. Okay, and the higher level, I mean, the efficient algorithms, graph algorithms like shortest path or nearest, these kind of things can also be realized. And because of the relationships at the same level as entities, doing that thing in a relational model would be a very tedious job. You have to jump on table on table on table and to understand what foreign key primary key relationships are there to get to the whole path of it. Here, it's much easier because it's stored in that way. Okay, it provides an abstraction for the uh, user because user only sees the graph data model and can understand what actually is there. There may be a case that you model in graph, but you actually store in some in other ways. So user don't need to understand how it is stored or how it is done. It understands the graph model with the abstraction, and he generates or creates his queries according to that graph. So the same thing which we were saying, easier and faster conversion of business thinking into data structures, because what business thinks are actually, I mean, if you see, human mind doesn't understand tables as much as they understand the nodes and their relationship. So in that way, it becomes much easier for business to understand and then uh, try to convert it into a business use case. So they perform low latency performance with the if the query complexity is big. So I mean later I will cover actually where they are lacking and what relational databases can provide and graph cannot. Yeah, and one of the major thing is that because the relationship is also there, the complex queries becomes faster, but quantitative queries will become slower. Okay. And the most important benefit of using graph data model is that they can be extendable without much of an effort, because it's just nodes and their relationships. So if there is a new relationship or new node coming in relating to other different entities, it can quickly be extended and uh, move on with it. In relational managing and creating those things, it's a uh, much tedious job as compared to the graph data models. Any more questions till here?
All good.
Okay. So now let's see the how we perform, how we actually do a graph data modeling. So let's say I just have a small whiteboard sketch in here. So I mean, people say that graph data models are very whiteboard friendly. Why it is so? Let's see. So what is here? I've just written that Hugo Weaving acted in The Matrix, directed by Lana Wachowski, who also directed Cloud Atlas. Hugo Weaving also acted in, and Tom Hanks also acted in Cloud Atlas. Okay, so this is a very simple example of a real world thing which is happening. And if I just quickly convert it into this and say that, okay, this is one node Tom Hanks, this is one node, this is another node Matrix, and these are my main nodes. Lana directed Matrix and Cloud Atlas. Tom Hanks acted in Cloud Atlas. Hugo Weaving acted in both. Okay, so this is one step. And in the second step, I start to mark it with the attributes and the labels. So Tom Hanks is a person and an actor. Hugo Weaving is also a person and an actor. Matrix is a movie. Cloud Atlas is a movie. He is a person and a director. And these are the relationships between them with specific roles. Okay, so this is now a graph data model. And this can, as it is, be stored in a physical level and can be queried upon depending upon the directed graphs.
Over here, shouldn't we create person as a node and then add tag actor and director top of it? Because it's same information you're storing at two different places, I guess.
Where?
Like the person information, name and bond, right? The same thing you're storing at two different places. So you're making actually director is also a person, right? Director or the actor are person. So we can create one person as a node and another movie as a node, right? To make it more simpler.
Okay, so there's one difference.
This is the instance example, like graph.
Exactly. Yeah, exactly. I would say if you look at an example of a topology-driven thing, or you want to design a topology, then probably you will create a node which is called person. Okay, and then you will create a movie. Okay, and that's all. Director, actor, that can be another label or another property as such. But this is a shift. You can do it like this also. Each Tom had entity. This entity is a node, which is a person, which is a actor, person actor. So this entity is not as a this entity anyway have to be stored separately itself, right?
No,
Tom Hanks wait. Tom Hanks need to be stored separately. Hugo Weaving and Lana also need to be saved separately as a separate instance, right?
This is a data example, not logical view of it, right? I think this is what the difference is. This is the actual how the data is saved, that example, how it will look like in a graph. But logically, when you are deciding a model, then there will be only two entities.
No.
That's schema. This is actually the instance.
Yeah. So, but rather, when we will define the system, in logically we will define this movie system. There will be only two logical nodes, right?
Yeah, well, yeah. If you talk about schema, there's only two entities here, and maybe multiple relationships. But the point of this system is you don't have to have the schema. So maybe Kuldeep will cover this I think sometime. Yeah, you can just start by creating this this data directly.
Yeah. So as Jadip, as I said that, I mean, if you want to have a topology or a schema defined, then probably you will do it in some different ways. Here you don't need actually to define a schema itself, because when you save this, this as such can be saved, and when you save this, you can query it by person, you can query it by actor or director, you can query it by acted in or something like that. So everything is a schema free kind of thing, and that's why it's extensible, and more relationship can be grown and can be made with time.
Actually, whatever I was saying, also same queries can be answered in the same speed, and it is also extendable.
No, it will not be an speed, because the schema, when here there is a no node called person. The node is an instance itself only tagged as person.
No, but these are two different things, right, Jaideep? A schema and actual instances, right? So when you query a schema, what you get is the answer about the schema. So they're not apple to apple here. So you can imagine this as if you relate to relational databases, one is a table schema, other one is the actual records.
These are records.
These are actual records.
But rather, when let's say there is a system now, somebody asked us to design data model, design the model for this. Okay, then at that time we will not design like this, right?
So the purpose of these databases is that you can't possibly imagine a schema upfront. So let's say the web is, if you look at web as a whole, it is evolving, right? Nobody had a schema of anything in the beginning. It evolved into something. So let's say a social graph system. It's getting created in two different continents in the world. So somebody in Europe is creating a social graph. They collect information about people and they define it in their own way. And similar concept is evolving in Asia, but we never agree upfront about how to represent a person. So we just start first. But most logically, we at some point in time, these things will link up. So, for example, countries, if you say, there is at least standard country names, and using the country names, suddenly these graphs, some nodes will start to connect to each other. So it is built for such evolutionary systems, but it also leads to a lot of problem because of not having schema upfront. Things are not standardized and things won't match. So such things are also there. So the spirit of these databases is to get things evolved first without a predefined strict model, and then comes the standardization after that, much later.
Raja, how we are saying that the way I'm saying is defining the schema.
So when you say a schema means you are talking about an abstract definition of a person, abstract definition of a movie. That's it. There is nothing more to it, right? You say the movie means movie must have a name. Movie must have when it was released. A person must have a name. Person must have a gender, where he was born, when he was born. So these are abstract definitions, right? But when you talk about actual instances, then you say Tom Hanks is a person. And if you are very strict about schema, when you create Tom Hanks, you will follow the schema and you will define those attributes. You will say name, where he was born, when he was born. And by strictly adhering to schema, you will not add anything more. You won't say anything less.
No. What I was saying that there is a person and there is a movie. What information you want to save in that? That's a different thing, right? But only there can be two nodes, right? Person and the movie
Okay.
in this
Yeah,
system.
that's the definition of a schema. Hmm? So, so if you take relational table, let's say you have a person table and a movie table. Person table will have million records. Movie table will have million records.
Mm.
Here, this example is talking about those million records. Each of the box here is talking about one record.
Okay, so can you go to the previous example? Not this one, the one at the start. Yeah. Over and over also, Raja, we are viewing at the logical level, like project, person, organization, department. We are not working out at a number value, right? Or we are working at a particular record.
So, yeah, here in the right hand side, you are looking at a particular record. When you say person ID 100 10,000, name is Jane, you are looking at a record here actually.
Oh, okay.
Mm.
Okay.
Okay. Okay, moving on. So there are basically four building blocks: nodes, relationships, labels, and properties. Okay, so as we have discussed, also nodes are the entities, the real world entities, which can be represented through a node, and relationships are actually the connectivity between these two entities. Okay, labels are provided to the node. So each node can have one or more or zero labels also. Okay, properties, nodes can have their own properties, and relationships also can have their own properties. So with the same example, so basically these four are the nodes, okay, and these are the properties for each one of them, like title, start date, person ID, first name. So these are the properties, and these are actually the instance of that as an example. And now these are the relationships which can exist in between them. And this role one, is actually a property of this relationship. Okay, so you can see it from here that one node can have more than one relationships to one or more nodes. It can also have more than one relationship between two nodes, same nodes, and it can also have a relationship to itself also. That is also allowed in this. Okay, so this is very basic of the graph data modeling, and this is the way to do it. I mean, create the nodes and then try to find the attributes, create the relationships, and try to define the properties of that relationships if available, and then try to label the nodes if any existing relationship or any new relationship is formed in there. So few basic tips which we can use is actually to write your queries. Okay, so to start, when you start data modeling, the first step is to write your queries which you want to get answers of from a graph model, prioritize them, then build the model, okay, and test it out that what query which you want to run is being successfully answered by the graph which you have created. And then if not, then you can refactor it anytime. So that's what how graph data modeling is done.
By prioritize them, what do you mean?
Prioritizing, prioritizing means which query takes, I mean, which query is more important to a business than to an query which is not very important, but it's a good to have. When you write business use cases, some use cases would be to a very high potential that these need to be answered in a correct way, or these need to be answered to the full. And some queries that okay, if it is not possible, it's okay, but if it is what is possible, it's good. So it's just prioritizing those things. So when you prioritize the queries which you want to have answers for certain, your modeling will bend towards that to answer those questions. rather than starting through a query which is not that important to the business.
We are thinking that the model cannot answer 100% of the questions. That's why we are prioritizing it.
Any model, I don't think, can answer 100% of everything. But some queries, if you design, because you are designing, right? So if you model, you while modeling, you can take care of how fast that query can run. Okay, so how much nodes, how much relationship we have to get that answer. Can we reduce that relationships to an extent that this prioritized query can get a little faster, and the non-prioritized queries can result in a little slower output also.
Okay.
So that's what prioritizing is. Yes. We cannot say that all the real-time questions are answered by a data model or not. But when you model, where you try to answer all the questions, but definitely you will prioritize which are the most important questions to answer, to get an answer from.
Okay.
Maybe at the time we decide on creating a new relation, if the query that is going to be most frequently used by the business,
yeah,
we might end up creating a new relation between those kind of nodes.
Yeah.
One more question, Kuldeep. I'm just trying to understand the building blocks. So, from what I understand, the nodes can have a set of properties, relationships can have set of properties, but labels, what I think is inherit the properties of the nodes. They don't have their own properties, right?
No, they don't have their own properties. Their properties, they actually are, you can say, a small tag to every node. So these come into the picture when you say that, okay, this person, okay, he's working in a organization, in a project in an organization, and he's also a blogger who writes this, who owns a website, and who writes this blog and talks about this topic. Okay, so let's say there is an extension of this graph also here. Okay, now a person who wants to query for the blogger, no need to understand the project and department and organization. He will start with the blogger label and just query the graph from here. Getting my point?
Yeah. I mean, my point is the properties of that label will not be present in the same node, but might be present as some other relations to that label. Like you're saying, if someone
more like an alternative name, right, Kuldeep?
Yes, right. So it's basically a tag. So these properties are of this node.
Yeah.
So these will always remain this node.
One way to imagine this is a label is another attribute of a node, where it has a specific meaning. The moment you say label, it represents alternative name. That's all.
that's right. But one thing I want to understand here. So the moment we say that there is a new label to that node, but the set of the properties for that particular node, now it is a label, remains the same. Any new properties we want to add or any new relations we need to add, we'll have to create new nodes for that, which might be of a different type of node.
Not really.
So you mean
just an alternative name only. So it's like you have a Java class, but you can only have one name for a Java class. But imagine that if you are able to have alternative names for the Java class, that's all we are talking about. Everything else is the same.
So it's an alternative, not an extension.
Not an extension. It doesn't change the meaning completely. It's just an alternative name.
Okay.
Okay. So should I move forward? Now we are clear for these four building blocks.
Yes, Kuldeep.
Okay. Now I hope the how is clear. So we will jump into the when part. So when we should use graph data model is to when the data interconnectivity is quite important. So basically, if you see the social networks and other what should other examples would be social networks and other things where actually the relationships are also important. You cannot leave out relationships and just focus on entities. in that cases, it's good to use a graph data model. Okay, storing the actual entities and actual data in any form in the physical layer can be different, because graph modeling can be done for relational, NoSQL, and obviously graph databases also. Okay, so following that point, the complexity, when the complexity becomes more complex, when you have much more relationships and relationships after relationship, a friend of a friend, or these kind of things that come into picture and that takes precedence in your business requirement, then uh, graph data modeling is the best way for you out. And because of that complexity, and because that the relationships are taken into precedence, the graph databases are also uh, high performance in such kind of scenario. And the flexibility is always high because you have a uh, you can say an option to extend your data or extend your model to add new nodes and new relationships. Okay, so the flexibility and agility comes from there. Okay, so I will try to make a point through this small chart. When you say a data complexity on the X and data quantity on the Y, okay, so quantity means there are huge volume of data for entities, and you need to process it, and you need to let's say traverse throughout the database for uh, some information. In that cases, actually big data and all those solutions are much more faster and helpful, but they don't take much care of the relationships existing between data that is left to the application side. It's for fast retrieval of the huge amount of data quantity. Okay, and GraphDB actually comes in here where the complexity is quite high, but if the volume grows, your graph become more and more complex. And since your graph becomes more and more complex, the querying of graph and the amount of subgraph you are querying also increases. So that's why the performance is tend to decrease when the quantity is going to increase. So that's how in the real time, in the real world, I would say graph data models or graph DB are actually used where a used for a module or a section of business where the relationships are important. Rest all the huge data and the data processing is actually taken care by big data itself. So people tend to use the combination of big data or NoSQL and a GraphDB over that. Is it clear, or any questions?
So this way, the social media kind of use cases, they will not end up using the exact definition of GraphDB, but somewhere between big data.
Yes. So I mean, that's what I mean. If you see in the Facebook or Twitter also, they use GraphDB for a specific purpose. They don't use it all the way to save everything inside that. They use it only when the relationship or connectivity or tagging or all those things need to be taken care of. Rest all the huge quantity of data is stored in some different way.
Okay.
Okay. Should I move forward?
Yeah.
Okay. So after this, let's look at this graph database space. So here actually non-native means, so there are two things, right? Graph storage and graph processing. Okay, so graph storage, non-native is that they don't store in a uh, graphical way. That means they don't store in a node and relationship way. They store in some different way, but they provide some mechanism to consume it as a graph. Okay, and graph processing. So these graph processing means the querying the graph node by node, path by path, relationship by relationship. So this is what actually graph processing. So if you see this FlockDB, which was the Twitter DB. It's between in here somewhere, where not completely on the graph storage and non-natively on the graph processing also. So this Allego graph is totally native. It stores the actual nodes and now I think they also provide graph processing, but which is not very efficient till now. So this Microsoft Trinity, Titan, Infinity Graph, they don't store in a graph native storage. They store in some different way, but they provide graph processing capabilities over what they have stored. Okay, so these are the databases actually Neo4j, Affinity, OrientDB. These are the things who store also in a graph format and obviously give the graph processing capability on top of that. Okay, let's look at on the in other angle also. It's a simple Venn diagram. So LPG is actually linear property graph. Okay, RDF is actually a linked data format where things are stored in subject, predicate, and object kind of way. Triples. And then this is our document databases and Q value store. So if you see this is quite new, Azure Cosmos DB, which actually falls into somewhere here. Okay, so the complete graph databases are Neo4j, Tiger Graph, because they provide the storage mechanism as graph and processing mechanism as graph also. Okay, any question on this?
Good for me.
Okay, so so we can now go into any other questions which we have. So before going into that, we just need to quickly give you 2-3 points on what's the good side of the graph database and what's the bad side also. So good side, we have seen that what is flexible searching and indexing. In graph database, the relationships are also indexed. So that's why the performance on the search and traversing comes fast. The bad part is, as I said, processing high volumes of transaction data is not good to use graph database in here. Similarly, for the large volume of analytical queries. Okay, and the major point is at the time of modeling, if the relationships are not defined correctly as per the requirements, then these graph databases, because there is not much focus on schema, they have the capability to go into a very messable architecture, and which is becomes very non-efficient at the end of the day. So the relationship between entities have to be defined very efficiently at the first place. So these are the few drawbacks of a graph database. Okay, so that's all from me. Any questions or?
I'm good.
One question. I mean, it's not a question exactly, but it's a thought that came to my mind. So, I mean, in relational DBs, we have thought of merging two different DBs with two different models, wherein we find the dependencies and all, try to solve that, and maybe come up with a new relational data model. But in the case of graph model, if you're trying to create a new model by merging two existing graph models, it will be creating a new, I would say, a new graph model as such. I mean, taking the
Yes, it will be creating a new graph model, but it's actually a simplistic union of these two. So which nodes relate to which node in both the models, you can just connect them and you are up and running. So you don't need to spend much more time on because both are graph and both are flexible to extend, right? So it's just the connection between the two model graphs. Let's say there are 4 entities in model 1 and 5 entities in model 2, which needs to be connected. Okay, so we can quickly just make these connections, or if there is a need of another entity, another node to be created, we just create that node and connect it quickly. So I mean, it's easier in this compared to relational.
And from where I see, mostly it'll be like, because the entities are already defined, and in two different systems, the entities have their meaning. Mostly, merging two would be like having relationships between those entities of the different worlds. Creating the relationship would be the challenge if you're trying to merge them. The entities will have their own properties always. That should not change.
Let's take one quick example. I think this problem is what linked data initiative is trying to solve. So number one is the entity must be uniquely resolvable, right? So for example, let's say Sharad. Let's say I start to document about Sharad in here in Singapore, his professional aspects, and then Sharad's father starts to document about Sharad, the non-professional aspects of Sharad. He's not unprofessional, but non-professional. Let's say his demographic details of Sharad, his father is documenting. Now, one thing that is important is that the entity called Sharad, we must uniquely at least agree on a unique name for Sharad. So, Linked Data Initiative has something called URI, Uniform Resource Identifier. Imagine that there is a registry in the world where I go and look for Sharad Gupta, and it is going to give me a URI, which looks like HTTP www.person.com/Sharad, let's say. So, as long as there is such a registry, Sharad's father will start to create all the data about Sharad using that as the key. And I also use the same key and create my own side of the database. Now you will suddenly see that these two things can merge, although they are in two different databases across the continent. All of a sudden, if these are resolvable and linkable, and especially if the URI is HTTP based URI, suddenly it becomes web linkable also. So I document that Sharad works here in Singapore, he stays here, and he's so and so professionally, and his father documents his demographic, and now the knowledge adds up, and now 1 + 1 is more than 2 in this kind of a scenario, right? So graph databases allow these kind of not so pre-prepared evolutions. If you have to do it in the relational database, first of all, me and Sharad's father should sit together and create a schema first, and then the schema must be created in a database. And then when we start to put the records, the relational database will force us to stick to the schema. Obviously, there is definitely something good that comes from that, because we can query this much efficiently, etc. But in the other way, where we don't have to have a predefined schema, let's say Sharad's father is very good in describing things demographically. He doesn't have to agree that schema with me, where I am good with describing Sharad professionally. I don't have to agree with my schema with him. So we just start to evolve parallelly. All we have to agree upon is this particular URI name. So that's just the simplest example where graph databases really perform very well, more applicable here. So in the linked data world, they realized this, and then they start to create different groups of people like Yahoo, Google, Microsoft. They all come together and they create this kind of common URIs, common relationship names. For example, how do you describe a spouse of someone? Should you call a spouse? Should you call husband/wife? So there is a place where you can go and registry where you can query what is the standard URI to describe a spouse relationship. Now these things are evolving. Now you can imagine that if more and more people start to use the standard URIs to describe the entities and the relationships, you can have knowledge evolving from different places and then suddenly linkable by the web. This is what we call the world of linked data. Yeah.
Okay. This will definitely make the merging of big companies, for example, Facebook and WhatsApp, they have different kind of data. I mean, linking that data would be easy with that.
Absolutely, absolutely. So you have social graphs from different places, the wall gardens. If you want to break through them, these technologies will help in that. Yeah, this is imagine that today Facebook and LinkedIn follow a URI named to represent us. All of a sudden, you have LinkedIn having professional details, Facebook having our personal the, those details, and suddenly all these things merge together and becomes a big knowledge base. Okay, good.
Okay.
All good. Then we can stop recording here.
Yeah. Thank you.